my lab, I promise you I'd have a trick question that if you just went by color, you'd get in some trouble. Now, color varies according to, again, we talked about all the different colors of quartz, impurities, okay? And some of those metallic minerals, what type of environment did it dry in or create? Was it created in a dry environment or a wet environment? Now, things that contain iron tend to be strongly colored, okay? They tend to be dark in color, red in color, never clear. This is not a great way. Never, I had a student pick up a purple mineral and say, oh, this is purple quartz. And like, no. Does it scratch glass? And he tried to scratch glass. No. Okay, well, it is not purple quartz. So don't fall into the color trap, okay? Because there's a lot of purple minerals that are not amethyst or purple quartz. All right, there's another property that we always note what the color is. And I always note, is my mineral transparent, translucent, or opaque? And I call this the shower door test. Okay, people that are exhibitionists like transparent shower doors. Okay, pure glass, you see everything, they see everything. Okay, now people that are a little bit more shy, maybe they like translucent. Okay, light goes through it, you can see somebody's in the shower, you probably can't tell if it's a boy or a girl, etc. Or if you're really, really shy, you want a shower curtain that lets nobody look in and you don't look out. So it's impervious to light or opaque. Now, for instance, we're going to talk about a mineral called calcite. Calcite is the building block of limestone. And calcite, I have samples sitting on my desk that are transparent, I have other samples that are translucent, and I have other samples that are opaque. It can come in all three forms. It's just something that we note. All right, streak. Streak is the color of the powdered mineral. And typically in lab, we just use a streak plate. You see if your mineral scratches glass. If your mineral scratches glass, you do not run your mineral over that non-glazed shower tile, okay? Because you will just powder the porcelain. Obviously, if you have a harder mineral, we could get a harder substance. We could get a diamond file, and we could look at the color of the powder. This is much, much better. Now, I'll show you guys a slide here in a second about hematite. Hematite is iron ore. Okay, we would have no steel if it wasn't for lots and lots of hematite. And if you guys remember that banded iron formation we talked about earlier, that's a hematite. Okay, now that comes in a lot of forms. Check this out. It can come in red, like a dirt clod. It can come in hard red on the right. It can come in gray. It can come in that silvery stuff. It always leaves a red-brown streak. Okay, that doesn't vary, even though that color varies completely according to what type of an environment it was grown in. But its streak doesn't vary. It's always red-brown. All right, luster. Now, you guys, is it metallic or non-metallic? That's really all you have to state, but there is shiny metallic, there's dull metallic. And, other than metallic and non-metallic, you come up with your own names. I've had students say rainbowy, okay? Rainbowy means pearly opalescent to me. Dirt cloddy. Dirt cloddy means dull or earthy to me. So, you come up with your own names, and that's fine. But luster, is something metallic or is it non-metallic? Is it shiny? Is it glassy, etc.? All right, here's fool's gold, and not all that glitters is gold, and not all that looks like gold is gold. There's a couple tests you could do really easily and figure this out. We have a lot of this pyrite or fool's gold at Folsom Lake, so I have a lot of students bring this in and say, I found gold, and I hit it with a hammer, okay, and it's not gold. You can actually hammer gold into a thin sheet. This shatters. All right, cleavage or the sledgehammer test. Now, you guys are at a big disadvantage, not only being online, but being students in a time of terrible budgets. When I was first a geology student, we would sit in a geology lab with a huge sledgehammer, a pair of goggles, and hundreds of samples of minerals, and we would just smash, smash, smash. Cleavage is the ability of a mineral to break along planes of weakness. So if I have a cubic mineral and it has cleavage and I hit it with a sledgehammer, all of the little pieces will be cubes, okay? Now remember that quartz crystal, if I hit that, it will not break to look the way it did. It will shatter, it will fragment, it will be in shards. It has no cleavage, okay? Now, Cleavage is usually breaking along planes of weakness or weaker bonds. Ionic bonds have excellent cleavage because they are weak. Now, a lot of minerals actually have a mixture of ionic and covalent bonds, and so they will cleave along those weak ionic bonds. Now, there's a lot of different ways. If you guys are in lab, you're going to spend a lot of time talking about cleavage. Again, if my life depended on it and I had to identify a lot of minerals, I would use cleavage. Cleavage does not lie. One direction of cleavage, it would peel off like sheets. Two directions of cleavage. I'll show you guys some pictures of this and talk to you a little bit about it. Three at 90 degrees would be a cubic. 3 not at 90 would be a rhombus. Okay, do you remember that? Pull that one out of your memory banks. And then there's a mineral that has 4 directions of cleavage. It's kind of cool. It looks like an 8-sided dice, if you kind of know what that looks like. All right, here's just some examples. On the left-hand side here, that purple mineral is fluorite. And that's in your water to strengthen your teeth. And that's that 8-sided dice. So you're seeing kind of the top part of it with the 4-sided pyramid. So it has 4 directions of cleavage. Right in the center is halite, or table salt. Okay, sodium chloride. It has cubic, or 3 at 90. And to the right of that is the calcite. And the calcite is a rhombus. Or 3 not at 90. All right, so my big warning, and I learned this too, is that, does it pass the sledgehammer test? And if you take a beautiful crystal and you whack it with a sledgehammer and it does not break in the same form as the crystal you started with, it does not have cleavage, so you don't mistake that. Okay, so with the quartz, you're going to end up with some shards, and I believe I have a picture. We'll look at it. Okay, we call that fracture quartz fracture. So you hit a beautiful 6-sided, pyramid-topped quartz crystal, and you end up with just ugly shards. Now, quartz has a very specific type of circular fracture called conchoidal fracture. You guys, make sure you know that name. Think about it. If you've ever seen, look on your windshield. If your windshield has a ding on it, right? You drive on the freeways around here. I've never had so many dings on my windshield as I have since I've been up here. And look at it, it's always circular. Okay, the rock that hit it wasn't necessarily circular. It's because it's a quartz windshield and it breaks in a circular pattern. Now, quartz has fracture because every single bond is covalent, or very, very strong. So when it breaks, it doesn't break according to weaknesses, it breaks randomly. All right, I did take a sledgehammer, I smashed a big beautiful quartz crystal, and look what I got, okay? It did not pass the sledgehammer test. This is that conchoidal fracture. And you can see the circular breaks along the edge, etc. We'll talk more about conchoidal fracture when we get up to the obsidian, okay? All right, density. How much mass divided by volume? How much does it weigh, in proportion to its size? And it's a density. It's a packing thing. It's a how heavy is the element thing. I only use this in lab as what I call, again, the heft test. The metallics. A lot of students have trouble. Is this metallic or is this non-metallic? I'm always surprised by it. And sometimes we can actually use that heft test. Man, this thing feels heavy. Oh yeah, it's probably metallic, okay? So, densities are not something at this level you have to memorize a whole bunch of, but if I put a metallic sample in one of your hands and a piece of quartz in your other hand, I bet you could figure out which one was which just by density, which one was heftier. All right, hardness, really, really important property. This is the ability to scratch or be scratched, or resistance to abrasion. Harder minerals, like diamond is the hardest mineral of all. Nothing scratches it except for other diamonds, and it scratches all of the other minerals. The harder the mineral, the stronger its chemical bonds. If you have a very soft mineral, talc, we're going to talk about talc, it's got very weak chemical bonds. Okay, covalent are those strong bonds. Ionic are those weak bonds. Now, some of the ones that are kind of in the middle of this scale have a mixture of ionic and covalent. All right, now Dr. Mo. Dr. Mo, there's 3,500 minerals, you guys. I don't know them all. I do know some people that do, okay? I don't know. I don't care to know them all. But he just took 10 minerals and he just put them in order of, who scratched whom. Now, this is not a mathematical scale. Talc is not 1/10 the hardness of diamond. Diamond's a lot harder than that. And so, also because there's 3,500 minerals, there's lots of minerals that share, the number. So, what is that called? Graphite, pencil lead type stuff. There's some of it that could be at a 1 or a 2. So these are just some typical minerals that we would find. I come across, I think, all of these except for the diamond at some point out in the field. And just according to how hard it is. Now, there's certain tools. If you guys look on the right-hand side, our fingernails, you're going to see a lot of geologists scratching things, okay? We're not scratching it just scratch an itch. We're scratching it because that tells us about its hardness. Now, my fingernail and your fingernail has 2.5 hardness on this scale. So that means that we can scratch gypsum and talc, but we cannot scratch calcite with our fingernail. But a penny, okay, a penny or a piece of copper sheeting will scratch calcite, gypsum, and talc, but it won't scratch that fluorite. Okay, paperclip. A paperclip will scratch fluorite and the softer ones, but it won't scratch apatite or potassium feldspar. So you can kind of see the scale and the tools that we use. And obviously diamond is the hardest. Okay, now you guys, I've been in lots of labs where we've had diamonds. Not all diamonds are, jewel quality. Industrial diamonds, they cost like $5. They're really ugly, but they scratch everything, so it's pretty cool. All right, now those properties that we were just talking about are properties or characteristics that you test pretty much every single mineral for. But these are some properties that are really only useful for identifying one mineral specifically. Okay. Taste. Now, yeah, I've come into labs and I've had students lick every mineral. That's gross. That's not hygienic. Don't do it, okay? Because only one mineral will taste like table salt. Now, striations. I got a slide. It's really, really cool. Striations are these really straight lines that every time a student, I show it to them, they, oh, you went into the, into the shop and you got out some sort of a tool and you etched these lines in. And they're like, no, I didn't. These are due to the regular repeating internal structure. And I've got it on the next slide. I'll show you guys. And if I find striations, that tells me I have the specific type of feldspar, okay, a plagioclase feldspar. All right, we always have a magnet sitting around, and I've had students open up drawers and just see what minerals the magnet sticks to. Don't do that, okay? That's not good. But if you get to a point, you're like, wow, I think I have magnetite. Gee, I wonder. You stick the magnet on it, and the magnet sticks, because magnetite. Now, we're going to talk more about magnetite, because that's a really important mineral. All right, double refraction, also known as beer goggles. If I can find a transparent calcite mineral, okay, the calcite's the rhombus and it's, calcium carbonate, and if I put it on a piece of paper that has writing on it, I see double. Okay, and so it's called double refraction, and that's a property that only the transparent calcite would show. Okay, if I took that same calcite crystal and dropped hydrochloric acid on it, okay, it will fizz like crazy, because every time I do that, I actually release carbon dioxide that is locked in that structure. Okay, so calcite's pretty cool. It's got the rhombus, it's got the double refraction, and it fizzes with acid. Now, you could actually blindfold me, and I'd probably be feeling some cleavage, but I could actually feel some of the textures and just the feeling of the minerals, and I could probably identify a few of them, but not a good thing to do unless you know what you're doing. All right, here are those striations. You guys see those really beautiful straight lines? You also see some of that iridescence, or as the student calls it, rainbowiness. But see those really straight lines? Those are part of the regular repeating internal structure. We're going to talk more about plagioclase feldspar. If you go on in geology, you need to be able to identify this mineral. And, boy, if you come across these striations, you know what you're dealing with. All right, you guys, we are going to now learn about minerals and mineral groups. And what we have to do is we have to look at what's available, okay? And the 8 most common elements on the Earth's surface are OCIL, fecanacmig. Now, if you guys go onto the PowerPoint, there is an audio file. You need to listen to that because I explain all of this. You're going to need to know it. And if you learn the little saying, OCIL, fecanacmig, look at that. O, oxygen, Ci, silicon, Al, aluminum, Fe, iron, Ca, calcium, NaC, there's Na, it would be sodium, K would be potassium, and Mig. So OCIL, fecanacmig. Say it to yourself a few times. You're going to get it. It's really, really easy. Okay, and here it is. These are the 8 most abundant elements on the Earth's surface. Now, if you look at this slide right here, oxygen and silicon make up about 75% of what we find at the Earth's surface. So when we start talking about the main type of minerals that we find on the Earth's surface, or the silicate minerals, it's not really a surprise. Silicate minerals have a chemical formula of SiO and then varying number of O. Okay, OX is what I'm going to call it, because O could be 1, 2, 3, 4, 5. So SiO. It's not really a surprise because it makes up the majority of what's found on the Earth's surface. All right, so silicate minerals are the most common form of minerals. Now, you guys, this is really important because these, the very next thing we're going to do is we're going to get into rocks. Remember, minerals are the building blocks of rocks. And the next type of rock that we're going to get into are igneous rocks. All of you have seen at least a video of a volcano erupting, or you may have a piece of granite in your kitchen. Okay, that is 100% made up of silicate minerals. Every volcano is erupting silicate minerals. So silicate minerals are really, really important. Once again, in that PowerPoint, there are audio files. I also have an extra video on this, and I also have a voice thread. You guys, you can't get lost. Keep going over this stuff. Make sure you understand it. And look at the in-class assignments too, because the in-class assignments will kind of let you know at what level you have to know this. Now, the silicon oxygen tetrahedron. Okay, now kind of ignore the chemical formula. It's SiO4 for a second. And this has been pulled apart. We have silicon, the little blue guy in the center, and 4 big oxygens surrounding it. Now, silicon has a +4 charge, and each of those oxygens has a -2 charge. So think about this. If you have $4 in your bank account, but you write checks for $8, you're -4. And this has a -4 charge. So if you remember back to our stability talk, in order to become stable, we need to add 4 pluses to this, okay? And so, or we need to get this to 0 or no charge. And so we're going to go through a lot of different processes to do this. All right, this looks scary. Make sure you go back to the original PowerPoint and listen to the audio file. Okay, this is what we're learning. Now, the good news, you guys, I had to learn. See the idealized formula? I had to learn that. I'm saving you from having to learn that. The only one you have to learn is that bottom one, SiO2. That's quartz. Okay, but you are going to have to learn most of this other material. You're not going to actually, this is Earth Science 10. I'm not going to make you know the cleavage. My geology students have to know the cleavage, and they actually have to know a few more of the chemical formulas. And you're not going to have to draw those terrible models here on the right, okay? But we're going to try to explain what's going on here, okay? Because this is really, really important. And so listen to the audio. Also watch the supplemental video. I put that together where it's just a video of me and a piece of paper that will kind of walk through this here in a minute. All right. Now, if you notice that oxygen silicon tetrahedron, okay, so remember it's depicted in the top picture. You can see the kind of in lighter gray 4 circles that represent the oxygens. That little dark small circle in the center represents the silicon. So right there I've got my -4 charge. Now, in order to make a molecule out of that, or make a mineral out of that, to bring those, it's already a molecule, but to bring those molecules together, I'm going to need to add 4 positives. And what we're going to find out at higher temperatures, okay, those 4 positives are going to be iron and magnesium. So that could have been magnesium or iron there, but they're each +2. And right there, I have now balanced the negative charge. Now, the other thing that we can do when we get to quartz, what we're going to do is something called polymerization, or sharing of oxygens. We're going to make covalent bonds. Check that out. I took 2 isolated tetrahedrons, and now they're sharing 1 oxygen. And every time, when the temperature drops, these more complex bonds can happen. And by the time we get to quartz, all 4 of those oxygens will be shared, and we won't have a negative charge. Okay, but what's going to happen, the top one is my very first example, the quartz is the bottom example, but you saw a lot of minerals in between. Okay, and what's going to happen there is that we're going to have those covalent bonds, but we're going to still have a net negative charge until we share all 4 oxygens. Okay, so we're going to bring in iron and magnesium, especially at first, and then later on some other minerals, or other positively charged ions to create these other minerals. Okay, so my job is going to be to try to explain this to you. All right, now make sure you watch that other video. I don't want to keep repeating stuff. This is probably plenty long. Going to crash iTunes U. The very highest temperature mineral, if you kind of are looking at that sheet that you have, is olivine. And olivine is my isolated tetrahedron. Remember, this is happening at the highest temperature. I'm too high temperature to start sharing oxygen, so the only way I'm going to get these isolated tetrahedrons together is to neutralize them. So bring in some irons and magnesium to get them down to a zero so they can come together. Now, olivine is olive green and it's glassy, and so it's kind of funny that this is the densest and the, quote, darkest of my iron-rich minerals, iron and magnesium-rich minerals. Okay, really pretty mineral. All right, now as the temperature drops, check out the little picture on the bottom left. It's called a single chain. Okay, and if you look at it, you've got the isolated tetrahedrons, but between each of those, we're sharing one oxygen with an adjacent one. And so the chain would go on basically indefinitely up and down direction. Now, the only way to get these chains to stick together, they still have a net negative charge, is to use lots of cations. Now, I have a less of a negative charge, but I still have a negative charge. So I'm going to bring in what's available at this high temperature. It's iron and magnesium to glue these together. Remember osi-alphecanacmig? Okay, the alphecanacmig is what glues these together, and at high temperature, iron and magnesium is what's available. Okay, now this mineral right here is called augite or augite, sometimes people call it. It's in the bigger group pyroxene, and it's usually kind of a greenish black, and it's a single chain. Okay, and what's kind of cool, you guys, you're not responsible for cleavage. But if you kind of imagine if I had a whole bunch of these things like hanging from the ceilings like salamis, the ionic bonds would hold each of the salamis together, and then we'd have row after row and column after column. And so if I hit it with a sledgehammer, it would break 2 at 90. Okay, so that has that specific cleavage. All right, now think about it. You have 2 salamis hanging down, the temperature is dropping, and so what's happening is that every other oxygen between those 2 hanging salamis hooks up. And so they are now sharing even more oxygens. My net negative charge has decreased, but I still have a negative charge, and I'm still pretty high temperature, and my ions that are available are iron and magnesium. So they're gluing these structures together. Now this is a very cool mineral called hornblende. Okay, it's in the big group amphibole, and hornblende's cousin is kind of naughty. It's got a naughty cousin named asbestos. Okay, hornblende is not dangerous, but asbestos is not pleasant. Now, just because of a little bit different in geometry, this will break to not at 90. It's got the 6120. Okay. All right, so here's just some beautiful samples of hornblende. All right, we are still cooling down. We're sharing even more oxygen. So remember those 2 double chains? Now we have sheet. Okay, and this is really kind of an important break. Again, I've got a supplemental thing on here. These are called the micas, but one of your micas is black, biotype mica, and the other one is pictured here is clear or white, and it's called muscovite. Now, you guys, it's pretty easy to remember B black biotype, muscovite. Muscovite is named muscovite after Moscow, the type locale, and I always think of White Russian, okay? So we've got the silicate structure here depicted with the molecular model, and then what's holding those together are basically kind of spread some jelly, some positively charged jelly. In the black case, it's iron and magnesium, but we're going to eventually run out of iron and magnesium, and then we're going to be using a white jelly, which would be the aluminum and potassium. So we're starting to use Al, G, or K, so alphecanacmig is what we have available, and we've just used up Phe and Mig, and so we're using up what's left, the positives, to hold this stuff together. Did you guys notice that alphecanacmig, they're all positively charged ions. They're perfect for this job, to hold together my negative silicate structure until I finally get to quartz that needs none. No positives. All right, here's just a depiction of it. Again, the bread part of the micas is the same. It's just the jelly in between it that differs. Whether it's a black version or a white version is whether it's iron and magnesium or aluminum and potassium. All right, what happens when we share all 4 oxygens? Well, ultimately we have quartz, or SiO2. And when you're sharing all 4 oxygens, SiO2, think about it. Si is +4, O2 is -4. That means 0. But something strange happens. We got the feldspars. Okay, what happens with the feldspars is they are aluminum silicates. Some of the Si, the silicon that's in that kind of oxygen silicon tetrahedron, are replaced with aluminums. Okay, not all of them, but some of them. Aluminum only has a +3 charge. Okay, and so what happens is now I'm -1. I still need positively charged ions. So there are 2 different types of feldspars. There's the K-spar, potassium feldspar, or the plagioclase, which has calcium and sodium. And if you guys went on in geology, the ability to identify your feldspar is so important because that will tell you at what temperature your igneous rock forms. So it's kind of neat. But they're really, really important, and they're misbehaving, and they're going to come back and misbehave some more. By substituting some aluminums for some silicons, they end up with a negative charge when they shouldn't have one, and so then they still need ionic bonds, positively charged ions coming in. Now, because of that, they have cleavage. They will cleave. Okay, remember quartz doesn't. It has fracture. All the bonds are covalent. But with the feldspars, because you have the ions coming in, you've got some ionic bonds, regular repeating, and regular repeating weakness means a plane of weakness to break along. So they have 2 at 90 is their cleavage. Okay. All right, and that kind of looks like a rhombus. That's not a very good picture, but that's the potassium feldspar. And remember the plagioclase feldspar was the one with the pretty striations that I showed you earlier. Those white lines running through your potassium feldspar are not striations. They're called lamellae. And if we had 2 hand samples in front and I could talk to you, you would be able to tell them apart real easy. All right, so yeah, silicate minerals dominate, obviously, but there are other groups of minerals. Okay, the second most common group of mineral are the carbonates, and we have already talked about carbonates. Remember, when we talked about the evolution of layered Earth's atmosphere, that first billion years or so of layered Earth, we had carbon dioxide in the atmosphere, and it went somewhere. And where it went was to forming limestone. And limestone is made up of the mineral calcite. Okay, and so pretty common. Limestone, dolostone, marble are carbonates. If you drop acid on them, they will fizz. Okay, another type are the oxides. Remember what oxidation means. It means rusting. Hematite, iron oxide, is the most common form. And remember, as soon as we started having life photosynthesizing on Earth's surface, it started to, actually it was probably in the ocean, but it started to release oxygen, which reacted immediately with iron, making lots of oxidized minerals. All right, I'm going to show you one called native elements. Now, you guys, trying to think, a diamond. Okay, a diamond is only made up of carbon. If you were to find native copper or a big gold nugget, okay, you're like, yeah, I found a big gold nugget. That's native gold. All that's in there is Au, or the element gold. But unfortunately, we find a lot of what are called ores, which are mixtures. So a gold ore would have Au mixed in with a lot of other rocky material. And so a lot of times you have to crush up tons of rocks just to get a little bit of gold. So it's always nice to find native elements. Unfortunately, they're not, the way that a lot of the industrially important minerals are found. And so we have huge mines for that. All right, here's a piece of native copper. Now, I hope you guys are in lab and you get to see some of the copper ores. One of the biggest holes in the ground is a copper mine. It's because, unfortunately, the copper doesn't come like this. We wouldn't need such a huge hole. And I think at the end I might have a picture of that copper mine. All right, now you guys, I'm not going to test you on this, but this is so important because at the end we're going to talk about, what can we do to help this earth? And, just recycle your beer can or your soda can. That's what you can do. Now, mineral resources, we have a lot of identified mineral resources. Things change. We call them reserves if they're identified but not quite tapped or completely tapped yet. Ores are usually metallic minerals that are mixed in with a bunch of other stuff. They're not in that native form. Um, Economic factors change. Yeah, you guys, when I was younger, we used to run over all these abandoned gold mines. When I was, I don't know, 20, gold was $300 an ounce. Gold is now $1,400 an ounce. So a lot of the old mines that were closed have reopened because there was so little gold and weak concentration that it wasn't worth it at $300 an ounce, but it is worth it at $1,400 an ounce. All right, here's the Bingham Copper Mine. If you ever fly into Salt Lake City Airport, okay, look around, because not only is Salt Lake fascinating, but you will see what was at one time at least the biggest hole, man-made hole on Earth. Okay, and that's because it's not native copper that we're finding copper ore in the form of malachite and azurite. Okay, and if you're in lab, you will become familiar with malachite and azurite, and you might look at it and say, how the heck does copper wire or a penny type copper come out of this? It has to be crushed, it has to be melted and separated. It takes a huge amount of energy to do that.